Hello, everyone. Thank you for coming to our session. We will try to not really overextend it, so we can now join the celebrations that are coming. And my name is Kristiyan Gostev from Bosch Digital, and I am Eclipse Kanto project lead, and with me is Vasil Ivanov, also from Bosch, and he is one of the Leda committers. So today we would like to present to you how we from Eclipse Kanto, Leda, and the SDV community team up to provide means for managing vehicle software. But first, I'll give the mic to Vasco, who will actually define what is the initial problem.
So, modern vehicle architecture is actually really complicated. Yeah. Of course, what I'm showing you here is not a real vehicle architecture because they wouldn't let me put an image of one because of IP reasons, but this is like more of a caricature to just give you an idea that this is a bunch of distributed components, and this has evolved during the production generations of modern vehicles to bring out these many different connection types, so Ethernet, CAN, LIN, FlexRay, and all that, connecting all these sensor zones into gateways with multiple CPUs, all doing different tasks in a vehicle. And generally, it's not the complexity that's the problem and the distribution of the system. The problem is that these systems are tightly coupled. So they're not only coupled on the hardware level, they're coupled on the software and hardware level. So the software that's supposed to run as an abstraction of over the hardware on top of it is actually coupled to the software itself. So what's the idea of SDVs? The idea of software-defined vehicles is to break this coupling somewhat by leveraging knowledge from IoT domains, from the IoT domain mainly, and the cloud-native domain, so we can move the complexity from the hardware mechanical and the mechanical domain to the software one. So, of course, a car is not a washer, it's not a smart home speaker, so there are some really, really strict requirements. So we want our applications to be, and our SDV systems in general, to be both safe, provably so, and flexible, so people can experiment easily with them, deploy new apps, play with it, and all that. So this is a very narrow intersection of those requirements that we have to navigate. So we both have to ensure isolation and safe behavior. All the runtimes should be as lightweight as possible. So even though in the SDV community, people call the modern ECUs high-performance computers, they're actually low-power time cores, so we can't put a whole Kubernetes instance on top of one of those and expect it to work smoothly. Even though, so we still, however, want to provide an easy mechanism for developers to deploy new components and update current ones. And this update mechanism should be adaptable because, as you show in the initial picture, there are many domains, and these domains are not necessarily updated in the same way. So updating a GaussCI container is not the same thing as updating a microcontroller that controls your seat ECUs, your seat. So we also want these systems to be highly available. So we don't want someone to push an update overnight while you left your car and went to bed, and only to find out the next day that it's bricked because of some magic update that happened over the air. So we have to be able to detect failed updates, and we have to be able to roll them back. So here comes Eclipse Kanto and our integration with our project Eclipse Leda. But first, I will just give you a brief overview of what Leda is. We're the integration point of all these domains. So we take technologies from the automotive and the software-defined vehicle domain. So the Cuvesa VSS signal specification, Eclipse Velocitas, Eclipse Cuxa, from the IoT domain, Eclipse Kanto, which Kristiyan will tell you more about, and some cloud-native foundational such as Containerd, OpenTelemetry, the Yacto project. So what's Eclipse Leda? Eclipse Leda could be two things. It's a quick start Linux image, so QEMU and Raspberry Pi images that you can just pick up, start hacking, experimenting with SDVs. So if you were at Kai's talk, you would have seen he was using an Eclipse Leda image, a quick start image directly on a Raspberry Pi. He didn't build himself a new special image for his Raspberry Pi. He just pulled one of the releases of Leda. And when you're done hacking, when you developed your app, you want to optimize your image for production, so ensure safety, ensure reliability, the image to be, you want to make the image lightweight. So since Leda is based on the Yocto project, we provide a meta layer called Meta Leda, which allows you to pick and choose exactly which components from the SDV domain you really want, and add on top of that your own requirements as recipes. So I'll give now the mic to Kristiyan to introduce Kanto.
So to really understand how Kanto fits in this picture, first we need to have some basic overview of what Kanto brings as a whole and what is this project about. So Kanto is a modular IoT software that enables the device for IoT with all essentials like cloud connectivity, digital twins, local communication, container management, and software updates. Kanto is also lightweight, containerized, connected, and flexible. And what all this means, it would be better to show you on the actual Kanto architecture. So let's start with lightweight. Why Kanto is lightweight? So all Kanto models that we see here on the picture are written in Go, and they are standalone decoupled services that you deploy on your device. Each service represents itself as a digital twin, so that's what the digital twin means from the previous slide. And also each service is not actively doing anything unless it's told to do so, besides the, of course, the system metrics who have to actually send telemetry data constantly. So this means that when you're not managing your device using the Kanto services, those services are idle and not consuming any resources. In terms of flexibility, as I said previously, each service is decoupled and standalone, so you really can choose which services to pick for your device. In terms of SDV and what Leda is utilizing, it is the container management and the component that I will talk a little bit later. For container and management orchestration, Kanto provides solution that is based on containerd, and it's really lightweight, and it also have digital twins capabilities like all other services. OH applications or OH management applications, this means container management, software updates, system metrics, file backup, and all that are coming with Kanto, are behind this local communication layer that is MQTT, Mosquito by default. And this provides a way that those components to work both online and offline. Also, in terms of cloud connectivity, Kanto gives many different choices. So we see that by default, Kanto can work with Hono and Ditto, the open source stack. And also it can work with the Bosch IoT suite and Azure and AWS services. So in terms of cloud connectivity, Kanto is already prepared for multi-cloud deployments. So this looks really nice, but the SDV community was not really satisfied with what we already had, because currently, with that architecture, we didn't have means to actually manage the software on the different domains that a vehicle has, right? Being different software domains like container or firmware, or different hardware domains like different issues in the vehicle. So this year, they brought up, the SDV community brought up the idea to Kanto, and that's how the Kanto Update Manager was born. And what is the Kanto Update Manager? The Kanto Update Manager is following the same architecture that all other edge management solutions and the components in Kanto are providing. It is a decoupled standalone component that is standing behind the local communication layer in Kanto. And it also have those different update agents that are coming separately and as another decoupled component that are actually the dedicated workers of the update process. And each container update agent is responsible for one domain of the whole architecture. The update manager have two main responsibilities. The first one is to report the current state of the device for monitoring reasons, which means that every domain is being reported, all the software that is installed on that domain is being reported back to the cloud. All containers with each their specifications, the firmware, etc. And the actual updating mechanism of the update manager is to receive a desired state from the cloud and apply this desired state to the agents so that your whole vehicle to have the required software installed that is in the desired state. So what does the desired state is actually? It is a JSON format, but I have wanted to show you here in more human readable format. So this is a simple state representation where you can see that all the hardware and the software domains are represented, and this could be what you're seeing in the cloud, or this could be what you want to apply to the device. So all the containers, all the firmware versions, or whatever you have proprietary for your vehicle can be represented in this way, and the update manager will then handle it. So a little bit more details about the actual functions of the update manager. So the update manager is responsible for the orchestration of the update. Right. First, it reports the current state to the device, receives desired state specification for all domains, then forwards the desired state of each domain to the appropriate update agents, as we can see here on the picture, and then it reports the aggregated feedback of the all update agents back to the cloud. So what is this feedback? This feedback is actually what is happening during the update process, on which state each agent is during the update project. Is it downloading the artifacts? Is it performing the actual update, or is it cleaning up after that update? And then we have the other components of this architecture, which is the update agent. And each update agent is responsible for the update of a single domain. Each update agent must implement a dedicated update agent API that is already open source, available, and documented in the Kanto project. It updates a certain domain inside the target device or inside any of the other hardware domains, not only the actual device on which Kanto is being deployed. It reports the feedback of the update process back to the update manager, and it reports the current state of each domain. So the current state that is being reported by the update manager is an aggregate state that is coming from all different update agents. Right? So by default, currently we have two open source update agents that are available to the community to use them. And what we have in Kanto is the containers update agent that is coming in our standard container management solution. So what is the purpose of the containers update agent? The purpose of the containers update agent is to receive a desired state and apply it over the current state of the device. So we have some containers that needs to replace the old one. And that's a very good user story that every PM would be proud of. And the simplest implementation would be to first wipe the current state and then apply the containers, right? But it's not, you agree that this is not a very good solution because it can only bring problems. So what is actually a containers update agent doing is that he splits each part of the update process to different states. It downloads the containers, then starts the updates, then it's cleaning up. And what is the most important in this case, what is actually the most important state that we need to handle and maintain is the actual working state of the device, right? We don't want our car to be broken because of the update. So if any of the states fail during the update process, the containers update agents provide means to roll back to the previous working state. Right. Another update agent that is coming by default is the self-update agent, which Vasil will tell you more about.
So yeah, the self-update agent is hosted under Project Leda. And in Leda, we want to do OS level updates, so flashing whole OS images. Solutions for that exist, and Rauk is one of them, so it's basically an industry standard way of doing OS level updates. The thing about Rauk is it doesn't care how you bring the update bundle to it and how do you trigger the update itself. So you can even bring the update bundle to Rauk via a USB drive and trigger it with a manual command line command. Of course, we want to do something smarter. So in Leda, we have, as Rauk expects, two partitions, one currently active and one dormant, which would be updated by Rauk, and a data partition where the update bundle would be downloaded. So when the update message comes to the self-update agent from the update manager, first the self-update agent downloads the OS image to the so-called data partition. This data partition is much larger, and it's a read and write partition. These two are supposed to be read-only partitions for the root file system. And then the self-update agents, once it's done downloading the image, triggers the update via the Rauk dbus API, and Rauk does its job. So during the update, Rauk continuously reports back the current state of the update, if it's successful, if it failed, and so on. So the self-update agent takes that information, publishes it back to the proper MQTT topic, which is then aggregated via the update manager and sent back to the cloud as a state. So this way, the self-update agent implements the high-level update functions for OS level updates, and Rauk is like the wall level. And this could be easily swapped with another solution, of course, but yeah, we're now working with Rauk.
Okay, and so those two are the update agents that really fits the open source, and for all proprietary reasons that may come with the vehicle, or that will come with the vehicle, a custom update agent implementation must be done, right? And to do so, it is not that hard, because all you need is a MQTT library to have MQTT connectivity. The message format is quite simple because each domain is different on its own, and so the payload is free. Then something really important is to check the documentation and see all the different MQTT topics that you need to send feedback or consume the desired state. And then the update agent must implement the state specification. So that's a lot of information, right? A lot of APIs, a lot of architecture diagrams, and we wanted to provide a simple demo that illustrates what is actually going on in the backend in more comprehensible way. So yeah.
Okay, so I'll tell you what? Sure. That wasn't the demo, but okay. So I will first tell you in short what you are going to see, because the demo could be a bit hectic. But yeah, a GUI app that we just hacked together connects to a Leda virtual machine and reports the currently running containers on the right. On the left, partial desired state messages, which each describe a single container, are loaded as JSON files. So this GUI could mix and match via checkboxes the containers you would want to deploy as a desired state. You press the deploy desired state button. You would observe a container called self-update agent, SUA, which is running as a so-called system container. This is a container that shouldn't be removed or changed by the containers update agent because it's an important system container. And yeah, the demo would show what happens when a successful update is deployed and when a failed update, so leading to different final states reported to the update manager. So yeah, I would just step through this video. I wasn't brave enough for a live demo. So yeah, here I'm loading the JSON container definitions. Then I'm connecting to the MQTT broker, and you would see on the right, in the current state table, that's moving a bit fast, you would see the current state. And then I choose that I want my next desired state to be a single container that cooks a data broker, and I try to deploy it. Okay, good. And now the update manager is running the update, so give it a bit of time to queue the old containers. Okay. Come on. Cool. And as you can see, the system container, the self-update agent SUA, is still active because it's marked as a system container. And then I want to download a new container that has not previously been downloaded on the system, the Hello World, the Hello World container from Docker. Yeah, I just let it run, deploy it. Yeah, here I'm showing this container. Okay, going through the update process, running, and again, you would see the final state would be completed. So everything went fine, no broken images, no broken containers, so the final update state is completed. And now I would try to deploy a container with a wrong image reference, here called not a real image, with the name obviously wrong. I try to deploy it, and then run the update. The message is published to the MQTT broker, and then we wait. Yeah, there we go, it's running the update, and then it would go into the incomplete state because the lower level containers update agent reported a failure state, and this was aggregated by the update manager as an incomplete update, so the cloud backend could take actions based on that. Cool. So what's coming next? For Project Leda, we're mainly focused right now on community building. Our 0.1 release official is going to Rise and Solid. This is not marked on the timeline, but yeah, this month we want to add as an initial test WASM runtime, just to play with that, because WASM provides nice isolation. Then we're going to have a hackathon with the CME students, which are going to develop actual vehicle applications for a real use case. Crash data diagnostics. And then in 2024, we want to integrate the Kanto cloud connectors, so we have the whole backend pipeline, more SDV blueprints kindly provided by Kai and the Eclipse SDV blueprint community, and more example use cases and more community building. So yeah, please play around with Leda and try to deploy your applications there. And now back to Kristiyan.
Okay, and just a few more words for the demo, and because I can't stress enough about this, but this was not the actual user interface that you have to do the updates, right? It was just for illustration purposes, so you could see what is going on the backend. So what is going on in Kanto in terms of these updates. So first, we will release the update manager and the container updates agent officially really soon. And then we are going to a bit more features around the whole bit with DDI integration, a little bit more cloud support, and so on. And we also started a partnership with Bosch Global Software Technologies, and with them we are currently developing an actual solution for the whole stack, all the proprietary update agents and means for updating an actual vehicle, cloud connectivity, and everything this have this open source Kanto heart in the middle to orchestrate it. So, thank you very much for joining this session. Please check out Kanto, Leda, and if you want to connect with us, these are our LinkedIn profiles. Thank you once again, and I'll be glad to answer all the questions that you have. Okay.
Do you have any plan to make the custom update agent implementation as a sample? For example, for the embedded environment software updating?
Yes, very good question. Actually, currently in Kanto, we introduced another repo called sample applications. We don't have currently the sample update agent, but we are planning to make one really soon. So, because this is actually really something that would be very useful to the community, so they can just start from there. Yeah, thank you.
Thank you.
Okay.
First of all, thank you for the presentation. Cool stuff. Could be maybe more advanced question for you regarding security issues. Connecting with the backend, it's obviously security thing. Can you maybe high level or say what's your approach to connecting with the IoT backend and also receiving the desired state from backend? You know, could be also corrupted, so you need also some kind of security. So do you plan to introduce some security things, or what's your?
Okay, this is very good questions, and I will go back to this slide of Kanto. So in terms of connectivity to the backend, all Kanto cloud connectors are using, even this one, are using MQTT for communications with the backend. And all cloud connectors have all the TLS and security features that the MQTT protocol provides, like encrypting the messages and so on. So the desired state will come through the cloud connector, through all the security layers, right? It is not in the actual update manager, but the security from the cloud and to the cloud is actually handled by the cloud connectors. And that makes sense?
Yeah, yes, and how is the initial bootstrapping, let's say, in a nearly production use case? Okay, because if if the vehicle initially connects with the backend, the URL needs to come somehow, right? And for instance, Azure IoT Hub or Azure IoT Edge asks you to do it manually, right? So, but it wouldn't be good for productive scenarios. So.
You either pre-configure the cloud connectors so they can know where to connect to, or in Kanto we have bootstrapping components which can be used for that kind of initial configurations.
Okay. One question from me. Do you have any options to get telemetry data, for example, during the update process? Because something can go wrong, and if those systems support that as well? By telemetry, I mean logs, things like that.
It really depends on the different domain, because in different hardware domains, you may not even have installed Kanto, right? You may also have the update agent. So if you have Kanto, we have system metric service, and you also have means to stream the logs from the containers and from the container management to the cloud.
Based on the question asked before regarding the security, I was wondering, and that might be a good idea, to is there an idea to make sure that the desired state has not been tampered with, something like a signature on it or something that could be validated?
That's a very good proposal, so sign desired state. Yeah.
So now next you're asking me to create a pull request, right?
Yes,
yeah.
exactly. Or at least an issue.
How would you position Kanto in the Eclipse community against OSGI that is now in there as well and doing somewhat similar things? Meaning updating software in other technologies.
What Kanto offers, and that the current OSGI, I'm not really in depth with that, but what Kanto really offers is that flexibility to choose what actually to install on the device. You don't need the whole Java virtual machines and the OSGI framework and the different bundles, but you can install all different Kanto components as a separate services, each one that you like. One example would be the vehicle with the container management and update management and update agents. Another example of this flexibility is what you can see on the Uniro boot with the robot, where there is the software update and the system metrics component and the cloud connectivity. So, yeah.
From your perspective, would it make sense to kind of create a unified API for software update between those two technologies?
What do you mean by unified API between the two?
I mean the update tasks, the cloud connector and the things you send to the software update agents are pretty much the same. So you have to say to the thing, get a desired state and report back to me that the update was successful.
Yeah.
And that's the same for both of the technologies, so it could make sense to unify those in a standardized API.
Yeah, but the APIs that are currently coming are all standardized and open source, and they are the same for all domains in terms of update agents and orchestrations of the update, right?
Who would do such a standardization? I mean, one option is always, as an open source project, you have de facto standardization by means of it becomes popular.
Right.
People start using it. Are you more thinking about a specification process like within the OSGI?
Yeah, actually in between, so kind of as the meta level that then would have OSGI and Kanto as implementations.
But who would do that?
Yeah.
So my short answer would be, they are currently doing that. If you want this to be adopted by OSGI, be my guest. That would be the issue. Or the other way around. I mean, if the OSGI world already has a great specification that does the same thing, you could take a look there.
Yeah.
I don't think
absolutely.
there's a need for more specification committees or something. My personal opinion.
Yeah. We actually may need more of this, the specification. Okay, more questions? Okay, if there are not more questions, thank you. Thank you once again for coming, and yeah, see you around.